Unable to hear me? Am I audible?
Yes, sir. You are audible.
Okay, okay. Sorry. No. Okay, okay. Good morning, everyone. Whosoever have joined just now. And all the things that we have learned till now, including every topic in linear algebra, they were all important from machine learning point of view. Whatever I have covered in SVD or let's say in matrix decomposition part, those are the only important aspects. Majority of them are important both from ML and your exam point of view. But there are certain topics which I have, not certain topics, actually, there is the last leg which I have intentionally not covered. It is not important from your exam, but it is very important from your ML perspective. We will take it up in lecture 12. This is how I have been doing all this while. So in lecture 12, when we will cover principal component analysis and the decomposition of matrices, big input matrix that you have in machine learning, or let's say any AI task, how do you decompose this? How do you find low rank decomposition of them? So we will be looking into it in that session. But from your exam point of view, whatever I have covered till now is all fine. So we are going to change from linear algebra to calculus. I would rather say vector calculus. It still is, there are some portions of linear algebra which would be involved here, but you will eventually understand that it is majorly calculus. So when I say calculus in today's session, let me tell you what we are going to cover. Sorry. In today's session, we are going to cover first univariate. Actually, calculus, if you think of it, is divided in two parts: differential or differentiation and integration, right? Integration is very seldomly used in the MFML portion because majority of the things that you will be learning, they are all dependent on differentiation. Okay. So this is what we are going to get into. So we will start with univariate functions and their differentiation. Okay. I'll just write different DF. Then we will go into multivariate functions, a function which are dependent on more than one variable. Okay. Those are called as multivariate. So we'll go into multivariate functions and how does the differentiation of those looks like. From there, we will learn about partial derivatives, how partial derivatives are used in gradients. Okay, and eventually, this is the portion which is of much use to you, both from ML and also from your exam. You are almost certain to get a 4 mark question from here, and we will cover that today. The idea is to actually give you a perspective of gradients today. And then, if time permits, we'll go into the third part, which is uh, when, let's say, when you think of a function has two parts, right? An input and an output. So basically, a function relates an output to the input which is given, right? So there are some combination which happens to the input here, and then you get to some output. What happens when input is a scalar and output is also a scalar? What happens when input is a vector? Let me not write it. What happens when input is a vector and output is a scalar? Okay. What would happen when input is actually a vector and output is also a vector? We call them as, this is most important. We call them as vector valued function. Okay. If time permits, we'll get there. Otherwise not. Vector valued functions, and the gradient of these vector valued function are called as Jacobians. Okay. I'll give you enough perspective about them. They might sound very alien terms right now, but you will understand them eventually. And these are some of the things that that are all related to calculus. Okay. Then because will be only getting next lecture, there are chances that I'll have an additional lecture because we are on lecture number 6. This is in your lecture number 6, as I was going through right now. They have also included in this lecture Taylor series. Okay. But Taylor series is what I will capture, or I'll help you out. Post we study Hessian. After Jacobian, I just wrote right. After Jacobian, we'll understand Hessian of a matrix. Actually, we'll understand Hessian of matrix from maximum minima point of view. How do you find maximum of function or minimum of function? Eventually, what we call as optimization, right? How do you optimize a function? Because this is important from your ML point of view to do gradient descent, right? So you would want to minimize the loss function of your machine learning model that you have chosen. So from that point of view, we will we will actually learn first Hessian, or let's say we'll first learn about optimization. Optimization. We'll relate how optimization is related to Taylor series, or actually gradient descent is derived from Taylor series. So you will eventually understand the importance of Taylor series, and this is one of the most profound ideas in calculus. You will understand that. I'm not going to cover this in this session today. I am going to cover this in the next session. But if time is there and we get enough time today, I'll definitely cover some portions of it because this is one of the most profound ideas in machine learning. Okay. And Taylor series is because of a lot of people might not tell you gradient descent is actually there because of Taylor series, and you will eventually understand why, where it comes from. Okay. But these after Taylor series, let's say the next session is majorly dependent on Taylor series, Hessians, and on optimization, right? That would be lecture number 7. Now, only thing that we'll be left with would be back propagation, and linearization. These are the two topics. Linearization is also dependent on Taylor series. Actually, Taylor it's a part of Taylor series. Back propagation is what you will have some understanding today. So I'll give you some understanding. So eventually what I'm trying to say is if I'm not able to cover, let's say this is what I plan to cover today, right? This is lecture number 6. If I'm not able to cover uh, this portion in next session, or if there are chances that let's say if I'm not able to cover even this entire part today, then I'll have one more extra session. That's what I was trying to say. But anyways, I think that I will require one more extra session, which would be in the next week, because I have to cover 3 different aspects of it. But from your exam point of view, there are 2 different important sections. This one that you see and this one. Okay. So these two are most important sections, and the most important part is this gradients. This is what if you understand it well, you eventually are going to get somewhere around 4 to 6 marks. That is for sure. Okay. Questions before we start? No? Okay. Let's get started then. I will go on for, or this would be a run of next 45 minutes, and then I'll open up for your questions. So I'll mute all of you. Now let's begin derivatives. Some of you might already be well aware about this topic or whatever I'm going to cover in next 40-45 minutes. If you feel that it's something that you already know, where you're not learning anything new, you can go ahead and do whatever you would want to do. But and the idea is everyone should be onboarded to this, right? So, and there are certain things that you will eventually get to hear, which you might not be aware of. So stick to it if you feel. Now let's say that you are driving a car, okay? I'll just give an example of of what you or most of us might be able to relate to. Let's say you are driving a car, and in that car you have started from point A and you are moving to point B. Okay. And let's say that the position of the car at point A at time t, let's say the position of the car is a function of time t. This is basically the position of car at point A at time t. Okay. You already know ft is position of the car. Let's say you drive for almost h hours. Okay. You have taken a straight road from A to B and you have driven the car for h hours. Now here at B, you would be the position of the car would be ft plus h because you have already driven for h number of hours, right? The ft plus h is the position of car at point B at time t plus h, right? So ft plus h is position of the car at point t plus h. Now you have basically what I'm trying to say is the position of the car at A was ft, the position of the car at B is ft plus h. Here you have started from this position, here you have changed to this position. Now, if you have to say how much the position has changed, you will just write ft plus h minus ft, right? So the quantity that you see here, it's a change in position of the car from point B to A or A to B, right? Or how much you have actually traveled when you have traveled from A to B. Okay. Now, this is the entire displacement that you have now, or this is the entire distance that you have covered, right? Now, this entire distance that you have covered, if you divide by in how many hours that you have covered the distance, you will get to speed. Right? So the distance divided by time is speed. That's what you already know. Right. So numerator in this case, this tells you about how much you have covered or how much the position has changed, how much car's position has changed, how much car's position has changed, and denominator is how much time it has taken or elapsed time, right? Now, this fraction, as I've told you, this fraction is called as speed or more. This is called as average speed, right? So you can write average speed is equals to whatever I have changed divided by t divided by the time interval that you have. Okay. Let's say that you have this entire distance was eventually 100. Okay, and it has taken you almost 2 hours. So the average speed would be 100 by 2, basically saying 50 kilometers per hour is what you were driving for. But as soon as you reached B, there is a pop-up on your phone. Okay, and you read that there is a challan, auto challan generated. And that challan says that at time, let's say you started here at time 10 a.m. And auto challan says that at 10:38 a.m. your speed was 120 kilometer per hour and which is 20 kilometers more than what you should be driving. Okay. Now you are almost shocked. You already know that your average speed was 50 kilometers per hour. How in the world you have crossed 120 kilometers per hour? Where, right? Now, this entire thing that you see here, the entire fraction, okay? Now you know that in your car you have two different things. In your car you have an odometer and you have a speedometer. Okay. Odometer tells you how much amount of distance you have covered, right? It also always tells you how many kilometers you have drove and drive or you drove, right? Eventually. Speedometer tells you what is the speed of the car exactly at that moment when you're measuring it, right? Now, this entire scenario that I have just stated in front of you, the challan getting generated exactly at 10:38 a.m., that is instantaneous speed. Okay. Now, derivative if you think of this entire formula that I have written down here, or this entire fraction that I have written down here, ft plus h was your position you have reached. Ft was where you started, divided by h was your entire speed that you have had. If you have to capture instantaneous speed, you will just say that limit h tends to 0, because you want to, if h is 1 hour, you are basically measuring average speed. If h is 30 minutes, you're still measuring average speed in a confined window. If you keep shrinking h to a very small value, okay, almost 0, that's what this expression says. If you keep shrinking h to almost 0, this becomes your instantaneous rate of change. Instantaneous rate of change. Okay. And this instantaneous rate of change is called as derivatives, or it is represented as, let's say, uh, currently the rate of change of position, right, with respect to time dh. So this is what this is how you write it. But eventually, the speedometer that you have, okay, the speedometer that you have in your car, it measures the instantaneous rate of change, which is the derivative we are talking about. Derivative differentiation is instantaneous rate of change. What exactly is changing when you have the rate, the quantity in the denominator is shrinking to almost 0. What is the change? What is the change which just have happened in a fraction of a second? Exactly, almost like thousands of let's say, when you divide the time into 1,000 small units, in one of those units, what is the change which is happening? Okay. Now, there are two things that you need to understand. The top is telling you about change, right? Or you are, I told you about instantaneous rate of change, right? Now, this change is what we study in calculus. Calculus basically is all about the study of change. Study of change is called as calculus. Okay. Now, just to keep the general knowledge, keep the general knowledge check of all of us, which two scientists or which scientists eventually, I ask you, do you know or do you well know for calculus? Any one of them, can you name? Can you name any one of them? Newton. Exactly. Exactly. Right. So we know that I think you should, some of you who do not know about Isaac Newton, you should know about Isaac Newton. Sir, actually, I should call him Sir Isaac Newton, right? Because you already know the wonders that Sir Isaac Newton has done and the kind of things that he developed. I mean, we are nowhere around around him, because at the age he developed all of those things, it was almost like a miracle that he was doing at that time, given that you had so less resources at your hand. Then the other individual who was a German, we call him as Lebanese. Some of you might not know about Lebanese, but Lebanese have done immense amount of work in calculus. Okay, but anyways, you should learn about Newton and how he actually discovered calculus, because he was trying to solve a problem. So when he was solving that problem, he eventually discovered calculus to solve that problem, which is itself unique, or which is itself a very novel thing, right? So yeah, yeah. But let's say, how do you write rate of change? How do you write? This is what I have just written. Well, let's say there is a function which is dependent on one variable only. Okay, this is what I was telling you about. There is a function which is only dependent on one variable x. The input is x, so we write it as fx. Right. The derivative of this is written down as how does the function changes d of fx divided by dx. So this is how you eventually write, or you can directly write as df by dx. This is how you write the rate of change of that function with respect to x. Okay, because x is what it is dependent on. Input is x, whatever that function value is, that is what you are trying to change. For example, let's say that your function is fx is equals to x square. This is an important function. I'll tell you about what this function is and why this is important. But let's say that fx is equals to x square. Okay. Then if I have to write how does f, because it is entirely dependent on input x, right? If x is equals to 2, then fx becomes x square, which is 2 square. This is x. This is your fx, right? So this is input. This is your output. Right? Input is 2. Output becomes 2 square. Sorry, 2 square, basically, which is 4. Right. So now you see that how input gives you a new output, how output and input are dependent via function. This is a univariable function because you have only one variable out here. Right. Now the change of this function df by dx, the rate of change of this function or instantaneous rate of change of this function df by dx is equals to 2x. Some of you already know about it. But where in the world have we arrived at this? How do we arrive at this? How have I written down df by dx is equals to 2x? So in your slides, when I was looking at it, eventually I found that I know that some of you are really good in maths, but this expansion right now, whatever they have written, x to the power n, right? Let's say derivative of fx is equals to x to the power n. What that formula looks like, they have tried deriving it, and while deriving, they have used the expansion of binomial, which is not we'll be using. So let's eventually think more intuitively. How does that derivative? If this is what you will be using. This is not for all of you to actually remember or to devise the proof, but it is always good to know how did we arrive at that formula. Okay. So the rate of change of fx with respect to x is 2x here. But the question is how did we arrive at this? So eventually, let's say we have this function, right? Fx is equals to x square. Now you already know that what if for a small h, let's say x plus h, this function input is x plus h right now. This function can be written down as x plus h whole square. And by the definition of derivatives, that's what you have learned right now. We written it down like this: limit h tends to 0, or basically when h almost becomes 0, this change is called as instantaneous rate of change, right? Now, if I feed in these values here, you will eventually get x plus h whole square minus x square by h, right? And if you open up it up, it will get x square plus 2xh plus h square minus x square divided by h. Eventually, you will get, because this is all gone, you'll get 2x plus h. But remember, you had limit h tends to 0, right? So this is what will get applied here. H becomes 0. So if h almost becomes 0, it becomes 2x. Hence, the derivative of fx is equals to x square is eventually 2x. Now this is what you can also look into, or you can prove for fx is equals to x cube as well. Okay. I'll come back to your questions. I just write it down. I'll definitely come back to your questions. Let's say if fx is equals to x cube, in that case, what would happen? You can eventually write it in the same way, right? So limit h tends to 0, x plus h whole cube, a small change in the function, sorry, minus h cube divided by h. So if you expand this up, you already know what is a plus b whole cube, right? A cube plus b cube plus 3a square b, which is 3x square h in this case, plus 3ab square minus h cube divided by h, right? This now, sorry, this is x cube, not h cube, right? So this now becomes h cube plus 3x square h plus 3x h square by h. If you take h common from top and bottom, it would basically become, or divide both of them by h, it basically become numerator and denominator. So it becomes h square plus 3x square plus 3xh. Now, because you are applying or seeing this at h almost 0, right? This becomes 3x square. Now you easily relate to, because when you're discussing about x square, we reach to 2x. When we are discussing about x cube, we have 3x square. Similarly, x to the power 4, what you're seeing that there is a pattern here, right? 2 comes out in the front, it becomes 2, and then x reduces by 1 degree, right? That's what is happening here. 3 comes out at the front, then x reduces by 1 degree. So this is your function, okay? And this is the derivative of the function. By the way, derivative is also written like this. It's almost equivalent to writing df by dx. Okay. Now, for example, x to the power 4, it would be 4x cube. Similarly, if you go to x to the power n, you can write it as nx to the power n minus 1. So this is the formula that eventually is important for all of you. This is a formula that you will be using in all the while. Now, using this, if I ask you what is the differentiation of d by dx of, let's say, x, what that would be? Simple, right? Most of you already know about it. What is the, it's one. Simple, right? Yeah. But what is the differentiation of, let's say, my laptop is slow. What is the differentiation of, let's say, d by dx of, or what is the rate of change of one, a constant value? What it would be and why? Zero. Yeah, it's zero. But think of it, rather than looking into formulation, let's realize the essence of calculus, right? The essence of calculus is rate of change. Let's plot it out. Let's say that let's say you're talking about a function which is y is equals to 1. Now, y is not at all dependent on x. That's why if you write dy by dx, eventually that becomes 0, right? Because y is not at all dependent on x. If you have to plot it down, if you think of, let's say this is your y is equals to 1, right? And y is equals to 1 would be this line. Now, this line, if x changes, this is your x dimension. If you think of, if x changes, okay, if let's say, or if you think of it as, let's say that if you think of it as x changes 1, 2, 3, exchange from 1 to 2, 2 to 3, there is no change in y which is happening. Y is all constant, right? Hence, the rate of change of a constant with respect to any variable which is changing is 0. That is what the essence is. Okay. Now, you already know that derivatives are written down as like this dy by dx, or you can write it as f dash x, or you can write it as df by dx. Sorry, let's say the function is f, so you can write it as df by dx or f dash x, or in some of the books you will eventually see that it is written down as f dash only. These are different ways of writing the same thing. Instantaneous rate of change written as the rate of change of that function with respect to x, the f dash x, rate of change of the function with respect to x, directly writing f dash. That's, I mean, there are various different ways and people have written down in different types of books. But if you see any one of these, you resemble it as they're talking about the rate of change. That's all. Okay. Now there are three different rules, and these rules are important from your problem solving point of view. The first rule is the sum rule. And this sum rule is, it says if you have two functions, let's say u and v, the sum of those functions, if you have to derive, if you have to take the derivative of the sum of two functions, and let's say that these functions, they can be same, they can be different. But let's say that if you have to take the derivative of the sum of two functions, in that case, the derivative of them would be nothing but, remember I wrote it as f dash, it would be like u dash plus v dash, or let's say you can also write it as, let's say you have two functions fx and gx. Okay. The derivative of, or d by dx of two functions which are dependent on x, and these two functions, given that they are different, if they are same, eventually you'll add them up and it becomes one function, right? Let's say that it is different. Now, if you have the sum of two different functions and you have to take derivative of them, you will just take the derivative of the function, which would be d by d, or f dash x plus g dash x. Okay. Or you can write it as d by dx of fx and plus d by dx of gx. Eventually, both of them are same. This is the same thing. So this is the first rule that you have. If you have two functions which are written as sum, for example, let's take a simple example. Let's say that you have x square plus x to the power 5, right? Both of them are different. One is x square, the other one is x to the power 5. What would be the derivative of it? It would be 2x plus 5x to the power 4, right? So you'll take derivative of the first function independently and the second function independently and write them in the addition form. So this becomes your output. So this is the first rule that you have, which is sum rule. Similarly, you have a product rule, second. And we are still discussing all of these things from univariate point of view. We are going yet to get into multivariate, and you will understand all of these things from that perspective. Let's say you have two functions which are written down into as products. Okay, let's say f and g. F is a function of x, g is also a function of x. Okay, f and g are written down as products. In that case, the derivative of them would be first taking the derivative of the first function, keeping the second constant, then taking the derivative of the second function, keeping the first one for constant. Or let's say that you have the function written down as eventually fx, which is a function of x, gx, which is a function of x. You are trying to take the derivative of them. Okay, it's written down in a product form. This basically is, you first take the derivative of the first function, which is gx d by dx of fx plus fx d by dx of gx. Okay, so basically, if you have product of two functions, then you can write it like this. Let's say that you have something like mm, x cube into log of x. Okay, I mean, I have not told you what is the derivative of log of x, but remember, just for this moment, let's say that derivative of log of x is 1 by x. This is a simple formula that you can eventually derive, but and this is also related to Taylor series. You can derive it from Taylor series. But let's say that you already know that derivative of log of x is, d by dx of log of x is 1 by x, right? So now you have two different functions, x cube and log of x. If you have to take derivative of x cube log of x, then you will first take the derivative of first function. So log of x would remain constant. You will take derivative of first function, which was 3x square, right? Plus you will take the first function constant, take the derivative of second, which is 1 by x. So eventually your answer would be 3x square log of x plus x square. That's what it is. Simple enough, right? So this is a product rule, and this product rule would be more important when you will go into the third rule, which is called as chain rule. And this chain rule is actually used in your ML side of it while doing back propagation, while sending the information backwards from a neural network point of view. You will see that chain rule happening there. Okay, let's say that to eventually give you an idea of chain rule, let's say that you have a function which is like, let's imagine something which is hard to do via product rule. So let's say you have x plus 3x square whole to the power 100. Okay, let's say that x square plus 3 square to the power 100. This is what you have as function. Okay, now you can think of you have only one function raised to the power 100, but to find its derivative, it would be very difficult. Okay, first thing can be like you can expand it to the power 100 and then derivate each and every term using some rule, which would be very, very difficult for anyone to do, right? So in these cases, we easily take certain assumptions. Okay, then that's what you will understand as chain rule. So let's assume that x plus 3x square is equals to u. Okay, u is equals to x plus 3x square. Now, eventually, your function, which is, let's say that this is y, okay, y is equals to x plus 3x square whole to the power 100. Eventually, your y would become u to the power 100 because you have assumed u is equals to x plus 3x square. Now, your question was asking, let's say your question was asking, what is the rate of change of y with respect to x or dy by dx? This is what you had to find out. But now, because y is dependent on y is dependent on, if you think of y is dependent on u and u is dependent on x, right? So y is a function of u and u is a function of x. In these cases, how do you do derivative? You just take the chain rule as if you have to find dy by dx, then you will say first, how does y changes with respect to u? Because that's what it is dependent on. So dy by du, okay, this is y, into how does u changes with respect to x, du by dx. This is what is called as chain rule. Now to solve this problem, you have to find out first dy by du. Okay, dy by du is u is equals to u to the power 100. It would eventually become 100 u to the power 99, right? This is what it would be. Then you will find du by dx. U is this, right? This part, du by dx would eventually be 1 plus 6x, because if you take derivative of x plus 3x square, it's a sum rule, right? X, you will first take derivative of x, which would be 1. You'll then take derivative of 3x square, which would be 6x. So then you will write it in this form, product form. dy by du is 100 into u to the power 99 and 1 plus 6x. You feed in the value of u, which would be 100 x plus 3x square to the power 99 into 1 plus 6x. This is that answer that you have. Okay, but you are almost not going to get these types of questions. I'm just telling you about, because we are moving in that direction. You should be able to understand how we actually reached these points or how we eventually got to these points, right? So if you think of chain rule is just saying that if y is a function of k, let's say that y is a function of k and k is a function of x, and let's say x is a function of t, then you can write it like, if you have to find the derivative of how does y changes with respect to t, because y is not directly dependent on t, indirectly dependent on t, right? So you can write how does y, first y changes with respect to k. So you will write dy by dk. Okay, then you will write how does k changes with respect to x, dk by dx. Then you will write how does x changes with respect to k, which is b dx by dt. Okay, so this is the chain rule. Now, where is it important? Just to help you understand also from another point of view, because we took that example of the car, right? Remember, we had that example of the car. We're moving from one position to another position using a car that you have. Okay. Now, your car's fuel consumption entirely depends on fuel, on speed, right? So fuel consumption is dependent on speed of your car. The more speed that you will be having, let's say you are driving at 120 kilometers per hour, eventually, or more than that, if you are accelerating more, you will be ending up, you will be consuming more fuel, right? So fuel is dependent on on speed, but let's say speed is dependent on how hard you press your pedals, the acceleration pedals, right? So fuel is dependent on speed, but speed is dependent on pedal. So eventually, if you would want to calculate what is the rate of change of fuel with respect to pedal, you will just write df by dp, which would be the rate of change of fuel with respect to speed into the rate of change of speed with respect to pedal, right? That's what this is eventually your chain rule, right? And where is this chain rule important? This chain rule is important because remember in your neural network, I don't know how much they have covered in neural networks in ML or in the other subject. Neural networks is you move, or let's say that you have neurons arranged here, right? You have information going into from this position to, let's say this is an output neuron. So you have input neurons here, you have some hidden layers, and then you have output. This is a simple neural network that I have drawn. You have two inputs. You have, let's say this is x1, this is x2. Then this is where you combine your inputs, right? Hidden layers is just combining them in a linear way and then using activation function, which would basically change it to non-linear. And then basically what you are trying to do, you x1 and x2 are coming in, you're combining them here like w1 x1 plus w2 x2 plus some bias you will add, right? So this is what you will do. You eventually combine them here, and then you feed this value, whatever this value is, to an activation function. Activation function basically is a switch on, switch off mechanism. It eventually propagates the signal only when the signal's value is more than a particular threshold, right? So this is basically there. Activation function is there to make or bring in more nonlinearities. Nonlinearities. I'll tell you about it in later sections why and how activation function brings nonlinearity. But see here what is happening. Activation function just propagates the information to the next layer, which is your output. So eventually, what is happening? You have an input, and you have a hidden layer, and then you have output. Output is dependent on hidden layer is dependent on input, right? So if you have to find out how does your output changes with respect to hidden layer, so you'll just write do by dh. Then how does your out hidden layer changes with respect to input? You will write dh by do, right? Eventually, what is this? This is, sorry, di. Eventually, what is this? This is how does your output changes with this input, right? So you change your input. How does that change is mapped to what you see on the output, right? This is what you see in your neural network, and that's why this entire chain rule is important. Okay, and for doing back propagation calculation and various different types of things, you will eventually see that these things are really important. Okay. Now, just I would cover one important aspect, and then I'll open up for questions for all of you. Okay. And that aspect is, given that you are already aware about the simple formulation of x to the power n. Okay, and derivative of x to the power n is written down as nx to the power n minus 1. But this is not only the kind of function, univariable function that you have. There are many non-polynomial functions which are like sine x, or let's say that cos x, or tan x, or let's say log of x, right? Or let's say e to the power x. These are various different types of functions that you have. You'll have to find out what is the rate of change of this with respect to x, what is the rate of change of this with respect to x. You'll have to actually either do a proofing of them, or you'll have to memorize them some way, because there are chances these types of questions might come in the exam, and then you might not be ready with the answers. There are very rare chances. The chances are less than 10%, but eventually I'm telling you because there are chances, right? It's not zero probability situation. So the derivative of sine x is simple thing, which is cos x. Okay, derivative of cos x is minus sine x. Derivative of tan x is sec square x. Okay, this is 1 by x, then this is e to the power x. So the derivative of e to the power x is e to the power x itself. It doesn't changes. But these are some useful formulas that you should remember apart from this one. This is eventually important, right? But I am pretty certain that you will not be getting questions from this. You will be getting questions from partial derivatives, which is what we are going to start with next. But before that, let me open up for 10 minutes and get your questions. So we'll start with partial derivatives and gradient in a bit, but let's get to your questions first. Yeah, go ahead. Whosoever has any questions, you can ask. I see some of the questions in chat.
Hi, sir.
Yeah,
Uh,
questions.
uh, Questions regarding is like the how much derivative part means like how much like in 12th as we know their whole subject itself derivative like whatever formula you told that's enough for the this
Yes, that's enough for the exam.
yeah. Okay, okay, okay,
I
thanks.
see there are no questions. We'll get into the next part. Okay, and that is what is important eventually. So let's cover it in next 30 minutes. That idea is next. Yeah, yeah, go ahead. Whosoever has that question. I see someone raised. Yeah, Ravin.
Yeah, I just have one question. Like while calculating the derivative for 2x, we got the answer as like 2x where plus h, where h is very negligible. So the my
Right.
question is like why we don't add a constant as well, just like integration. Like whenever we do integration, we add one constant over there, right? So why we don't add a constant along with the that 2x? Because h
Hmm.
is still have some value, right, which is negligible, but still have a value.
In integration, there are two parts. First, there you have definite and indefinite. When you have indefinite integrals, in that case, let's say if you integrate fx, okay, and the idea of integration is adding things, right? And the idea of differentiation is making things, making looking at a particular function from a very small interval point of view. Okay, and the perspective is we want to make this interval so small that eventually the function becomes linear. Remember the first or second lecture that I told you. Every single thing, when seen from the point of view of linearity, becomes important. That's why you learn linear algebra, right? You want to see how linear relationship vary. Here in the calculus, we are also trying to see, we are the reason that, let's say there is a very complex function which is looking like this. Okay. Now, if you look at function value at this point of view, at this specific range, it becomes almost linear that there, right? So there are chances that a function is actually very and difficult, right? It is changing every now and then. In that case, if the interval that you are looking into is not minuscule, it is not very small, the function might not look linear. That is the first thing. That is the reason why we take h almost close to zero, or h exactly as equals to zero, because you want to look at linearity. There are so much non-linear things existing in the world, but we don't care about non-linearities. Every non-linear function become linear when you see it at microscopic level, and that's why we study linear objects or linear things, right? Second thing is, in indefinite integrals, when you integrate something, the idea of integration is adding up things, right? When you integrate something, the function could be, let's say, x, the function's value could become x square. Okay. Now, when you integrate x, or when you integrate x, the output is x square, but we add a c there because eventually, actually x square by 2, right? Eventually, What exactly is x square? It's if you have to plot it down, you can have, let's say, C as 0, wherein this is how it would look like. Okay. C as 1, this is how it would look like. C as 2, this is how it would look like. C as 3. Okay. So for every C value, the parabola, actually, this is the equation of parabola. The parabola would look same. It's just that you would have some offset here on the y-axis, and that's the value of c there, because you don't know where what you are evaluating in what intervals. You just know that because you don't know the upper bound and lower bound where you are evaluating. Okay, that's why you add a c, just for the sake of approximating it better, right? You don't know where and what range you are evaluating. Understand that the idea of integration is adding up things. Let's say there is a function and the function looks like this, right? And the idea of integration is the area under this function. Because if you add, let's say, what is the value of the function at this point, what is the value of the function at this point, what is the value of the function at this point, there are too many infinite values, right? You are adding up so many values. Hence, rather than adding every single thing in a continuous function, you just have someone has just discovered integration. You don't have to add up everything one by one. You add everything, which is adding everything is just like adding the area under that curve. But anyways, I don't want to get into the discussion of integrals. The simple idea is in your indefinite integrals, you don't know what is the range you are evaluating on. That's why you add a c there. Yeah, yeah. Go
So I
ahead, go
have
ahead.
a question
That
for
one question.
derivation.
Yeah,
Can you show any graphical representation to explain derivation?
yeah, yeah, yeah. We do have. Actually, lecture 6, derivatives. First thing, let me show you this first. This is what I drew last year for the last batch. I'll just use this. This is univariate derivative. Let's say you have function x cube minus x, or let's say sine x, whatever it is. Let's say x cube minus x. This is how the function looks like. Remember, this is on the right hand side. That is the formula that we have used, fx plus h, the small change in x, the function's value minus what was the function and value at that point x, and h is the interval, right? H is this interval that you see it as the green line. I can change this interval to whatever I would want, right? If this interval is 0, is this interval h, remember limit h tends to 0. If that interval is 0, the change that you are measuring, okay, the change that you are measuring will not, this entire change, which is represented here in this green line, right? This is h that you have. So if this becomes 0, you are basically a tangent to the function, and this is what you are evaluating. So differentiation is nothing but a tangent to a function, or measuring the slope. How does the function change? So if you think of at this point, if you take derivative, it just tells you how much change to that function is happening at that point, right? How instantly it is changing at that point. Because if you take the derivative, it will just say whether it is going upwards or downwards or whatever, right? At that point, it just tells you, because based on that, that slope value, the tangent value, the slope value, you will eventually get to see whether it is inclining upwards or it is inclining downwards. I'll give you an example on the board, but this is how you represent it visually. This is how you can see visually. Similarly, let's say there is a function sine x, right? This is how the change of sin x looks like, the derivative of sin x. Now, the most important part of derivatives is, see here, this is the part that you should learn. Remember that in finding maxima and minima, what we used to do was we used to find out at what exact positions the rate of change of the function is equals to 0. Okay. Because the rate of change of the function is 0, only at these 2 points. Think of you have a function like this. Sorry. Think of you have a function like this. Okay. Now the rate of change of y, let's say this is y. Okay. Y is a function of x. The rate of change of y with respect to x is represented like this graph. Okay. Now at this point, you might see that the change is high. At this point, the change is y. But think of these points that I'm highlighting. At this point, or at this point, or at this point, or at, let's say, at this point, or at this point. What would be the rate of change of that function at these points? What is the rate of change of y with respect to
Zero,
x?
zero.
0, right? Because the rate of change of function at that point is 0, eventually dy by dx is equals to 0. You know that these points are either the maximum points or minimum points, right? So to find out maximum or minimum of a function, we remember we used to do first take dy by dx is equals to 0, and then second derivative text in our 12th class, d2y by dx2, whether it is negative. Eventually, we'll come to that in the next class. But if this is negative, we used to say that it's a maximum, it's a minima, or whatever, minima, maxima, right? So based on that second derivative test, first we used to evaluate all those points where the derivative is 0. All those points right now for this function is these, this. But eventually you see that this is the only point where the derivative is 0. And this is a global minimum. There are many different minimums that you have. This is one minimum. This is second minimum, or let's say not that. This is the second minimum, right? And this is the third minimum. So basically you have three minimas. But out of those three minimas, one is global minima. Global minima is the minimum which is the lowest, right? So you have one global minimum and two different and local minimums. These are called as local minimum. To find out those, or to get to those points, the very first thing that you'll have to do is to find out where the function is actually equals to 0, or the rate of such change of the function is equals to 0. That's why we used to take that dy by dx. And this is the most important portion that you should be learning, right? This is the most important intuition of rate of change, because to find the function's maximum or minimum value, you will have to first get to this point. Okay. And this is what was shown here there on that visual. So you see here, the rate of change is 0 here at exactly this point. I mean, almost here, right? That is the point where the rate of change is almost 0. And this is the point that you will be evaluating either is it's a maximum or a minimum, or basically a non-conclusive point, right? So these are the points that you will be evaluating at. But good, this is good.
Sir, one question, follow-up question.
Mhm.
So this is differentiation, right? Like for example,
Right.
rate of change that we are seeing. Like for example, in the car, like if I'm going from point A to B, my speed would vary. It'll go up or it go down and all that, right? Finally,
Mhm.
when we do the integration, right? You said that's the area of all these yeah, derivatives that we have calculated. We're basically summing up, right? That area, that one.
Right.
So can you relate it to that example back, like how that integration fit there? Like,
Integration is the opposite of differentiation. It is, I mean, I cannot fit that back. There are two different examples, but think of it as
just trying
you,
to correlate between two. That's
uh,
all in a real example, right?
right, right. Think of it as, let's say you want to find out what is the total, or with that car example, what that would be. What could that be? For example, I'm not able to think of at that at this point how would I relate to, but definitely I'll write back to you. There are no examples that are coming in my mind to explain integral. I can explain it independent of that example, but not with respect to that example. Maybe let's say the total amount of fuel consumption that you have had uh, with time t. the fuel consumption that you have, or let's say that this is what you can say. Let's say the total fuel consumption that you have had. Remember that we had that chain rule. Fuel consumption is all dependent on the speed of the car. Speed of the car is dependent on the pedals. Let's say that you would want to estimate what is the total fuel consumption that you have had, right? And the fuel consumption is all based on the speed. And let's say that this is how your fuel consumption at different speeds looks like. F, how does F changes with respect to X, right? If you have to add over the total amount of fuel that you have consumed, in that case, what would happen is you will have to integrate this entire function F from wherever, whatever your start point was, as speed as 0, or let's say is S value as some 10 kilometers, and let's say here it is 80 kilometers, in between 10 kilometers to 80 kilometers. What is the total amount of fuel that you have consumed? So this is how you can relate to that as. So if you have to find out total amount of fuel consumed, you will just have to integrate this area. You will have to just integrate that function.
So
Yeah,
can we say it's a mileage of that particular trip?
It's
Like
not a mileage. It's basically an addition. Think of it as when you have to add multiple things. When you have to add, let's say if you are going out and doing a survey, for example, I'm just trying to tell you a different example. Let's say if you have gone out and have done a survey of people who have different heights and weights in the country, or let's say you are sticking to heights, you have taken survey of 50 different people, okay, and the height of people looks like this. The eventually it starts from, let's say, 3 feet and goes up to, let's say, 7 feet. There are more people, and of the distribution of these 50 people, if you draw it, and let's say that this is how it looks like, there are more people who are in between, let's say, 4 to 6 region, right? So this is your 4 to 6 region. Now, if you have to find out how many people are in between, what is the probability of people having a height greater than 6? What you will be doing is you will just integrate the function, because this is the function. Function is, you know that this is a normal function, that normal equation or normal graph. So you'll integrate this function from 6 to 7. So eventually to find out how many people are lying, or what is the possibility of people lying in between 6 to 7, then you can easily integrate that value. If you have to find out people lying in between 3 to 4, you cannot, because this is continuous. Think of it as, and I'm just telling you here, data can be of various different types. Okay, uh, you can have something which is discrete and continuous. When you have continuous data, in between 3 to 4, or let's say in between 3 to 3.1, there can be infinite values. It can be infinite number of people who have who are of height 3.1. Similarly, there can be infinite number of people between 3.5 to 3.6, right? This entire simple range. If you have to go ahead and add the the heights of people, of those many infinite people, it becomes a tedious task. You cannot go ahead and with a calculator and keep adding one by one, right? And that's why the idea of summing up using integration came in for continuous data. So integration is only defined for continuous variables when you have infinitely many values between the range. In that case, you cannot keep adding them, right? The only way that you can add them is via integration. That's why people discovered integration. Okay. So anyways, this is not a topic that we should get into. I hope you have got some idea about it.
yes, sir. Thank you.
Sir, there is
Absolutely.
one last question. As you showed in the graph, there are some local minima and one global minima.
Right.
So rate of change is also zero at global minima as well as in local minima. So how
Right.
to figure out, like how to conclude whether it is a global minima or local minima without seeing the graph?
See, the problem that we are going to get into is when you model a machine learning problem and eventually your rate starts decreasing. Okay. And your model stops here because it is not able to improve. You eventually will never know whether it's a global minima or local minima. So you just have arrived at a minimum most point. You would never know whether it's local or minimum. That is the first point. But remember why we have discussed about that function. Remember, I told you this function is important. Fx is equals to x square. Why is this function important? This function is important because this is a convex function. You might have been told about convex functions and convex functions, right? Convex functions are the functions with only one minimum. Okay. Now these functions are the mathematical definition of these functions are, let's say, actually the definition is very tedious if we look into the maths part of it, but let's take two different points on this function. Okay. If you draw a line connecting those points and the line is still part within a line is within the function, then that function are called as convex function. But think of functions like this. Okay. When you take two different points here and here, if you draw a line, this part of the line is actually outside the function. That this part of the line is inside the function. This is a non-convex function. Now the problem with non-convex function is, and this is what your neural networks directly gives you, it gives you a non-convex function. Now think of you're trying to minimize your error, right? An error looks like this. If you start from a particular point, you eventually can end up here. And that's why you try your model, machine learning model, starting with different weights, different values of weights. You start from here, you can reach to here. If you start from here, you will eventually get trapped here. But then there are cases, momentum based gradient descent on all of those things that you will be eventually learning in lecture number 9, 10, and 11. Entire lectures after 8, 9, 10, 11, they are all based on all of these things that you are going to learn. These are the things that you will eventually learn later on. Okay. But
Okay.
to
Thank you,
help you
sir.
understand that you will never be able to know whether you are trapped in local minimum or global minimum, the only thing that you keep trying is by having a different start point, am I getting to new minimas? Okay. If you are getting to new minimas, that's fine. But the most important part is if your function is convex, okay. If your function is convex, you have only one minima. You don't care about where you start from, here or here or here or here, wherever. You will always reach at the minimum, right? And that's why convex functions are important. And that's why you already know, you might already be knowing that MSE, mean squared error, is a convex function. Okay. Or cross entropy loss that you use in cross entropy loss that you use in classification problems. This is a loss function and classification problem. Both of them are actually convex functions. Okay. And that's why we use these convex functions. Okay. Once you know that it's a convex function, it becomes easier. And convex function has a peculiar property. If you can prove that the function is positive definite, or for that matter positive semi-definite. Remember what positive definite is. Positive definite property of positive definiteness is x transpose ax is greater than equals to 0. This is what the what positive definite matrices are. A is a positive definite matrix only if this entire thing, only this entire calculation that you're doing is all positive. X square is already positive definite because let's say whatever value that you can give into X, it will eventually become positive. Okay. So X, if you feed in X equals to -1, it becomes positive. If you feed in -4, it becomes positive. Right. But anyways, I'll just give you a 5 minutes, or I'll just tell you about a important point of view. Okay, this is what is important from in the next 5 minutes, and then I'll go to partial derivatives, which is basically we'll cover it in 20 minutes. But let's say that this is your function, some x square form, x square plus c form. Okay, somewhat. Okay, it looks like a parabola, and it's a convex function. Very first thing is if you see here, let's say that this is how your function changes. Let's say this is your error. Error function looks like this. Okay. Now, if you are, let's say, at a point, this is a point, let's say this is x is equals to 3. Okay. Now, at x is equals to 3, x square becomes, let's say that the function is x square only. Okay. Let's say that this becomes 9, right? The function's value becomes 9, which is the height of the function. But if you take derivative of it, x square. The derivative at that point it becomes 2x. At x is equals to 3, the derivative becomes 6. Okay. Now this derivative tells you, this derivative x is equals to 6. What does x is equals to 6 tells you? X is equals to 6 is some point all over here, right? This is 3, this is 4, this is 5, this is 6. It is just saying that when you are standing at x is equals to 3, to reach to more height, you just walk towards 6. At this particular point, derivative tells you at, at standing at this point, in which direction should you be moving so that the function's value increases. Okay. And now your derivative has told you that you have to move towards 6. And that's what derivative tells you. This is it is just said that you move towards 6 to attain more value, and this is the side of maximum increase of the function as well. But anyways, this is what you'll get to know in the next lecture. Let's say that you are here at this point, let's say -2, at -2. Let's say that this is -2. Now the function's value at -2 is 4. Okay, this is the function's value, but the derivative of the function is 2 into x, which is 2 into -2, right? Which basically becomes -4. Now now derivative tells you that to increase the value of the function, you have to, let's say this is -4, you have to move in this direction, right? Eventually, if you move in this direction, the value of the function increases, right? Because this goes up. That's why it is called as gradient ascent, right? And then you take negative of ascent to go down the valley. Anyways, I'll cover that in the next lecture. This is what would become more interesting when you learn about partial derivatives. This is all good. I'll just keep you muted for next 30 minutes. Okay. Now let's get into the real exam portions, which are important from your point of view. What is going to be there in your exam, right? So till now, we have been discussing about functions which are univariate, single variable functions. Okay, now let's look into functions. Let's say fxy, the function which is a function of two variables. There are two inputs, x and y. Let's say x square plus y square. Again, you can relate it to x square. This is a three-dimensional function which looks like a paraboloid. I mean, eventually, if you would look into the kind of thing that I'm telling you, this is the derivatives. I mean, by the way, this is that example 2x plus h, x is equal to 2x plus h, to visualization of that. I eventually did not cover it. I thought that I'll cover it in this. I'll share this entire thing with you. The idea of this is, why does it looks like 2x into h, 2x, right? Remember, you are adding, if you add small, this is x square. If you add small h to it, the entire square changes into x plus h. The sides of the square changes into x plus h, right? The small change, x plus h. There are three things that we're adding: x plus h on this side, x plus h, this strip on this side, and then h square. If you think of, we are adding two different of these strips, blue strips. That's why the 2 comes there. Now, when you think about cube, see here, you are eventually adding three different sections here. Remember, see here, there are three different blue sections. This, and this. That's all, right? These three different blue sections are getting added up in the volume of the cube. That's why the 3 comes up there. But anyways, this is what I'll give you as a thought to think of how can you visualize these functions, right? But herein, actually, I went there to help you and to show you the second part. So if you think of, this is your three-dimensional x square plus y square. Okay. And at any point, uh, it just tells you about how does the function changes with respect to both x and y, right? So this, if you think of it as here, partial derivatives. Let's say that this is your function, the three-dimensional function, x square plus y square. Z is equals to x square plus y square. Okay. Now, when you think of how does the function changes with only x, this is what it can be represented as, or let me show it to you in a slightly better visualized way, or it is actually going in that direction. But let's say that let me change the position slightly to help you understand. So let's say that this is how it changes in x direction. Okay. You can also see how does it changes in y direction. Right. So the rate of change is right now you are talking in terms of two in multivariate or in two variables in this particular case. You're talking because there are two variables. You're talking in terms of how does the function value changes with respect to with respect to the first variable, which in this case is x, then with respect to the second variable, which is in this case is equals to y. Right. If you have to reach to the minimum most point, think of it as if you have to reach here, you'll have to vary both, right? You'll have to vary both. That's how you'll reach minimum most point when you vary both, right? But and that's the reason why partial derivatives are important. You have a function which is dependent on two variables right now. If you take the derivative of this function, it is the same thing. Firstly, how do you write partial derivatives? You write partial derivatives like this. Del f, we call it as del f, rather than writing df, which is the total derivative case, df by dx. We call it as partial derivatives, del f by del x, because the function is dependent on two variables right now. How does the rate of change of the function with respect to x looks like? Okay, because you are evaluating only with respect to x, y becomes a constant, right? Hence, the derivative of this x square plus a constant, you already know the derivative with respect to constant is 0. Hence, this entire thing becomes 2x, right? Then you can write derivative of the function with respect to y. It eventually becomes y square. If you think of this entire function becomes y square plus c, because that's a constant. You are not evaluating its change with respect to x, you are evaluating its change with respect to y, hence it becomes 2y. Okay. Now, when you write it in a vectorized form such that you first write how does this changes with respect to x, how does it changes with respect to y. This is a vector, right? Because there are two values. First, the rate of change of the function with respect to x. Second, the rate of the change of function with respect to y. Okay. And at a particular point, they would eventually come down to a value like this, 2, 4. Now, a vector like 2, 4 is what? Think of it. A vector like 2, 4, let's say you are on a coordinate system. Okay. You are standing at this particular point. Let's say this is 1, 2. It tells you that to move have a maximum increase of the function value, you will have to go towards 2, 4 from standing at this. Let's say you are standing at this point, right? If you have to reach to attain a more maximum value of the function, you'll have to reach at towards this point. This is called as ascent. But you eventually want in your machine learning, you want to reach to the minimum most point, right? So you take negative of ascent and start moving in the opposite direction. And that's why this gradient, this entire vector that we have written down in vectorized form, is called as gradient of the function. Okay, gradient is eventually written down like this. Sorry, let me zoom it up. Gradient is written down like this: gradient of function f, which is currently a function of two variables. This is partial derivative of, or the vectorized form of partial derivatives. You just have uh, kept those two partial derivatives, df by dx, into a vector, and df by dy. Okay, so this is just a vector representation of your partial derivatives. Gradient is nothing but a vector representation of partial derivative, and the essence of the intuition of that is, let me show it to you. Now, if you see here, okay, think of you are standing at this point. Okay, this is what I was trying to tell you. The gradient of the function eventually tells you, let me minimize it so that you can visualize that. Now you see here, right? You have x and 2. These are the position that you are standing at, 2 and 3. 2 and on y coordinate 3. This is the position, right? Now, if you take a gradient of the function, gradient is nothing the partial derivative of the function, right? It tells you it basically is this point. This is that vector or in that direction. It tells you move in that direction to attain the maximum value, but you eventually you don't want to move in that direction because you want to get to the minimum most point. So this is that direction, right? Eventually, and the negative of the ascent side. So you start moving in the opposite direction. You start moving towards minimum. This is where your entire learning comes. How do you move into that direction? You start taking baby steps towards the direction. This is how. This is called as gradient descent. If you have to visualize it in 3 dimensions, for example, you eventually, oh, I have not added that, is it? Interesting. Just a minute. If you have to, or let me show it to you here. So let's run gradient descent. Okay, let me make it more slower than that. Reset it. See here. Right. You see that gradient vector getting smaller and smaller throughout the time. Anyways, I'll tell you about gradient vectors in the next class because that is the class that you are having wherein you will get the intuition of gradient vectors, why that vector goes on smaller and smaller, why you are looking at that vector only in 2 dimensional, right? If you think of the idea is here, you have a 3 dimensional function, which is z is equals to x square plus y square, right? This is a 3D function that you have. But when you take gradient is a vector of 2 dimensions. This eventually at a point would tell you 2, 4, or 2, 6, or whatever. This tells you a direction towards what you have to move to increase the function's value, right? It tells you the direction, and it perfectly maps to what we just learned for x square. Remember, we were at this point, and then at that point it said that you have to move in this direction. This function is 2 dimensional, but the movement that we are talking about is how which direction you have to increase the axis value so that the function changes or maximizes its value. Right now you have 3 dimensional function, you are mapping it to 2 dimensional vector, saying that in which direction you should move so that the function value increases. And that's what you were able to see there on that simple visualization, right? If I redo it, or let's reset it, and if you see it, this is the direction, but that direction increases function value, we have to go towards the minimum point, right? This is that eventually gradient descent thing. I'll show you much improved visual of these entire things in the coming classes. Those would be more interesting. But from your exam point of view, what is important? Okay, what exactly is important? Firstly, you understand that partial derivatives are nothing but when you have a function which has many variables involved. Let's say function of x, y, z, wherein it is x square plus 3xyz plus z cube, right? If this is a function, then your derivatives would be how does function changes with respect to x, how this function changes with respect to y, and how does function changes with respect to z. These are the things which would be asked in your exam. They will eventually give you a function like this, and this is how simple that is, right? You already know about how do you find df by dx given all of these things using the formula that you had, right? So let's say, for example, if you have to find df by dx for this function, firstly eliminate the ones which does not has x in it, z cube does not has, right? So you are restricted to x square plus 3xyz. Okay, the first one using the sum rule, x square would become 2x, right? Now the second function 3xyz, it has only 3x. The other parts are constants for it. So y, z, and 3, all of these becomes constant. It has only x. The derivative of x with respect to x is 1. So eventually you will be getting 3y and z. That's what you have as df by dx. Same goes with df by dy. Firstly, understand which variables are free of y. You have x square and y z cube. These are free of y. Only variable, only part of the function which is not free of y is 3xyz. Now 3xyz, if you there is only y which is dependent on y, right? So you have 3x and z. Keep it aside. You have only y. The rate of change of y with respect to y would become 1. Hence, this is 3xz. Nothing else. This would become 0. This would become 0. df by dz. There are only two parts. This part and this part, because x square is independent of z, right? So in that case, it would become 3xy plus 3z square. So these are partial derivatives that they will ask you. This is basically your partial derivatives. Okay, or they can ask you simply find the gradient of the function. Now you have the partial derivatives lined up. You just write it in that formulation. df by dx, df by dy, df by dz. Or they might give you find the gradient exactly at point, let's say 0, 0, 1. Now this is the x value, this is the y value, this is the z value. Feed in all of these values. Okay, this basically would become 0, this becomes 0, this x and z are 0. It would eventually become, this entire part would become 0, right? This part becomes 0. This would become 3 into 1 square, which is basically 3. So the gradient becomes 0, 0, 3 at that point. So they will ask you to evaluate gradient at a particular point, given they will give you a point wherein they will ask you to evaluate the gradient. This is very, very simple. Go ahead and practice all of these problems. You will not have any problem in finding out the gradients. Okay. But if you, yeah, I'll come back to you, Anup. I'll give you some time to discuss about it. But let's solve one more problem. Let's say that you have another question. Okay, let's solve something which is more of like the kind of problems that you might be getting. Let's say that you have f is equals to function of f is a function of a and b, 2ab, and let's say a is a function of uh, let's say x1 square. Let's say that a is a function of x1 square, a is equals to x1 square, and let's say b is equals to x2 square into x1. Or let's say that x2 into x1 square into x2. This is what that function is, right? Just to make it slightly more complicated. Okay. Now you know that f is dependent on a and b. F is a function of a and b. So basically f is equals to function of a and b. And a is a function of x1 and x2. B is a function of x1 and x2, right? So you have all of these things. Now, if someone asks you, let's say if someone asks you what is the partial derivative of f with respect to x1, or let's say that someone asks you, rather than writing directly like this, someone asks you, what is the gradient of f with respect to x1, x2? Now, f is not directly dependent on x1, x2. F is indirectly dependent. Therein, you will have to use chain rule, right? So the questions, there are chances that these types of questions are might come. So let's say you might be asked about the gradient of the function at or with respect to x and x2. So what you'll be doing to find out gradient, you'll have to first find out df by dx1 or df by dx2. But if you think of df by dx1, df by dx1 is df by dx1 is df. How does function a changes with respect to a? Because f is dependent on a and b, right? If you see there. So how does function a and function f changes with a? Then how does function a changes with respect to x1, right? Because we are talking in terms of x1 right now. Plus, how does the function changes with respect to a? Remember that b is also a function of x1. Not only A is a function of x1, that's what you see, but B is also a function of x1. So it would be df by dA into dA by dx1 plus df by dB into dB by dx1. So that's what you'll have to find out. Then you will have to find out df by dx2, which is df by dA del A by del x2 plus del f by del B into del B by del x2. Now, just to help you understand what it would look like, if you think of df del f by del f by del A would be what? F is equals to 2ab, right? F is equals to 2ab. So del f by del A would be what, right? It would be 2b. That's all right. Del f by del B would be 2a, right? You already have one part of the story completed, right? So this part is already there. Then you will find del A by del x1. You already know A is equals to x1 square into x2. So you can easily find out the partial derivative of del A by del x1 because x2 would become constant. You would only use derivative of x1 square, which using nx to the power n minus 1, it would become 2x1 x2, right? That's what it would become. And eventually you can practice these types of questions, right? So that's what I'm telling you. There are only two types of problems that can be framed here. Remember, problems wherein they will give you a function like this and they will ask you to evaluate the gradient at a point. This is the first part of the problem. I will give you some problems today to solve. Second type of problem could be problems with chain rule. F is a function of A and B. A is a function of x1 and x2. B is a function of x1 and x2. Now they want the derivative. They might want the gradient with respect to x1 and x2 because F is not directly a function of x1 and x2. You will have to first do the chain rule. This is what you'll have to first write down. Right. That's how the entire thing happens here. And this is what is important from your exam point of view. Okay. Now this having said that, all of these things which are there, let's say that you have a complicated function. Let's say that you have a function which says f x y is equals to x square minus 3x into sine x. There are less chances that they will give you these types of questions, but I would still say that let's say that you have something like this y into log of x. Let's say that you have a complicated function looking like this. If you have to take gradient of the function, if you have to find gradient of the function with respect to x and y, what you'll have to do? You'll have to gradient of the function is nothing but partial derivative of the function with respect to x, right? Because it's the function of x and y. Partial derivative of the function with respect to y, right? So this is what you have. You'll have to find out how does function f changes with respect to x. How does the function f changes with respect to y? Both of them, right? So if you have to write it down, which particular terms are independent of x? Right now, none, right? So you'll have to do it by parts. So firstly, you'll do the derivative of x square. It would be 2x. Then you'll have to do product. You'll have to apply product rule here. You'll have to first apply derivative of this, keeping sin x as constant. Then you'll have to apply derivative of sin x, keeping 3x as constant. Then you have log x. You already know the derivative of log x is 1 by x, right? So eventually this is whatever it comes out to be. I'm just telling you that there are very slight chances. There are less than 5% chances that these types of questions might be asked. But eventually these are the kind of questions which might get formulated for you. Okay. So what did you learn about it? What is the most important point of view? You have learned about gradients. And this is what you will have to remember in machine learning or AI for that matter for a very long period of time. Gradients are assemblies of the assemblies in as a vector. They are vectorized form of all partial derivatives. Why do we have to take it into a vector? Reason for that is when you look into a function and that function is dependent on two variables or three variables or whatever, If you have to, let's say, think of it, just think of it. I mean, let's say that you you are a very good trekker. You go to trekking every single time, but let's say that you are somehow uh, trapped in the night. Let's say the night is it is 1 a.m. You're trapped at the top of the mountain somehow, and it is all very foggy. Right? You are in a very foggy weather. You are not able to see anything. If you have to reach down, okay, let him make it a three-dimensional looking curve. Let's say that this is how it looks like, the terrain. Okay. Let's say that you are standing somewhere there. At this particular point, wherever you are standing, because you are not able to see anything, what would be your only aid to go down? Let's say this is your village or this is your base camp where you have to reach to. To reach to that point, how would you eventually, because you are not able to see, how would you eventually decide which way to go? What you eventually would do is maybe you will start tapping your feet in each direction, this direction, this direction, this direction, this direction. Think of it as this is that place where you're standing, right? You'll tap your feet at this direction, 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 all of them. And then you will take a sense of in which direction your height or the position of yours is increasing, right? You eventually have found out that this is the direction where the position is increasing. You take a turn back 180-degree, start moving in the opposite direction, and that's what the gradient descent does. So why is gradient important? The all of these taps that you're doing with your feet is to know the slope of the function at that point in various different directions. And some of these directions could be the rate of change with respect to x, rate of change with respect to y, and so on, whatever it is, right? And if this is a two-dimensional function, three-dimensional function, there are many different ways, infinite directions that are possible, right? Every direction would have how does both of them x and y changes with respect to your input values with whatever, let's say, how does the function changes with respect to your x, right? If you let's say if you are standing there this point, if you slightly move this side, your x position and y position both of them changes. If you start slightly move towards this point, x and y both of them changes if you slightly move. So basically you are evaluating how does your function value changes when you slightly move in every direction, right? Now because you're trying to look into how your direction change, how your function value changes, you eventually would realize because of the tap of the foot that you're doing which way it is steepest. Now gradient tells you the direction of steepest descent. This is what we'll prove in the next class. It's a direction of someone asked that question in the WhatsApp group as well. It's a direction of steepest ascent. Gradient is a direction of gradient tells you what is the direction of steepest ascent eventually. So you are trying to look into a direction wherein most of the change is happening, maximum change is happening, and that maximum change in the direction of increase of the function value. But you don't, your idea is to get to your home, right? Your idea is to get to your base camp. You will not go at the top of the Everest camp again. You basically want to reach to the minimum. So you start taking step into that direction, and this is what gradient descent eventually does. Okay, and then there are chances that sometimes you might get trapped in at a position. Now because you are all blindfolded, you are not able to see or whatever because of the fog, right? You are here at that point and you realize that you have reached the minimum most point. At that point everything is flat. You tap in every direction, you are not able to get any clue. You will just sit down there. This is what happens to your gradient descent problems, right? Because the gradient is not changing, you eventually get trapped there. Remember the point that we were discussing about minimums, right? You are eventually trapped here. Gradients are not at all changing there. So if the gradient is not changing, how would you get that idea which way to move, right? Because gradient descent algorithms are all blindfolded. They only look at the clue of gradient, in which direction the gradient is changing, and take the opposite direction, right? So if the gradient is all zero here, it will just get stuck here. right? And the only way to not get stuck there is if you're a heavy ball, think of it as you are rolling a heavy ball from here, right? If the ball is really heavy, because of the momentum of the ball, it might get cross this minimum most point, right? So then your momentum plus gradient descent comes into effect. This is what you will be learning in lecture number 9, 10, post your midterm examination. So your heavy ball basically helps you uh, evade, or let's say get past this minimum. Remember, you have the example that I used to take. You have these lakes formed at various different hilly regions, right? Just like your Pangong Lake. These are nothing but Pangong Lake, or these surfaces like them. They are local minimums formed at natural valleys that you see, right? So Pangong Lake is a local minimum that you have, but sea is eventually your global minimum. So every particular river that you see in your originating from Himalayas, they eventually take different paths. Whatever path they take, they eventually get to sea, right? Sea is their global minimum. So all the path that the river takes, it's all guided by gradient. I mean, you can get to that intuition, but rivers, they follow gradient descent. Natural analogy and natural language. Think of lightning, right? Lightning also follows the mechanism of gradient descent. Think of, I mean, I'm just opening up for all of you to get into how everything minimizes using gradient descent. Think of your LLM interactions. Every particular interaction that you do, what you would want is whatever input that you have done, you have given prompts, you have given, and the output that you have, you would want to minimize the difference between what you expect versus the output of them. And then you keep on doing that interaction many number of times, right? That interaction is nothing but the step taken in the direction of minimizing the difference between your expectation and your output. That's also is a gradient descent, by the way. This is, anyways, there is a different point of view, but there are many things that in nature which follows gradient descent, and everything is dependent on gradient. And that's why we study gradient, right? And gradient is what? Gradient is an arrangement, a vectorized form of partial derivatives. Okay, good. Yes, no. Sorry. I don't know how it happened. You will get to know about that. Okay. I will show you all the problems which you would be given, or those are given in your past examination. I'll give you some problems today to solve from this perspective. There is only one last thing that I have to tell you about before opening up for question. This is what my intention was to leave the class here at this point. Remember, you have input and output. The function relates input with outputs, right? The only thing that the function does is it relates your inputs with outputs. What if inputs are scalar, okay, and outputs are scalar? That it becomes is easier for you. You have only total derivatives. So let's say y is equals to 2x square. So you would just do dy by dx is equals to 4x. So input is one value, output is one value, scalar input, scalar output, no problem, everything is good. But what if inputs are vector? Inputs are vector, outputs are scalar. Scalar. Okay, let's say that you have inputs which are x1 and x2. They are some vector, and output is, let's say, some value y is equals to x1 square plus x2 square. Now, if you think of y is dependent on x1 and x2, okay, and y is basically a function of x1 and x2, which is like this because you have two different variables. Right now, it's a vector, right? The change in two, no, those two of those variables, input is a vector. But output is still scalar because you have, when you combine them, the function is x1 square plus x2 square. Whatever your value is, let's say x1 is 0, x2 is 2. So you have 0 square plus 2 square is, which is 4, which is basically 4. So output is a scalar, right? In that case also, when you take derivative, in this particular case, if you think of how does y changes with respect to x1, then you have partial derivatives in that case, dy by dx2. So basically gradients are, in this particular case, gradient for a vector input and a scalar output function looks like this, or partial derivatives form looks like this, because y is dependent on both of them. So what you eventually get, you have input which is a vector, you have an output which is a scalar, but the gradient is a vector. So input is vector, gradient is a vector, right? There are cases wherein, let's say the third case, there are cases wherein the input is actually a vector, okay, and the output is also a vector, okay. When the input is a vector and output is a vector, for example, let's say that you have uh, let's say that you have a function f1 is equals to x square plus y, okay, and f2 is equals to uh, xy, okay. Now you have this function, let's say that x square plus y is your input and xy is also your input. So your input is a vector. You see that there are two different values there. Output, based on however you would vary x and y, your output is always going to be a vector. Let's say whatever you would, let's say x is equals to 2, y is equals to 2, x square plus y, it would be 2 square plus 2, and then 2 into 2, right? So basic, eventually it becomes 4 plus 2, 6, 6, 4. This is a vector, right? So input is a vector, output is a vector. Now, if you have a situation like this, when you have input is a vector, output is a vector, in that case, what would be the gradient? Now, see here, f1 is equals to x square plus y, and f2 is equals to xy, right? In this particular case, the gradient of it would be, gradient is the assembly of all partial derivatives. The partial derivative of the first function would be df1 by dx, right? And df1 by dy, right? The partial derivative of second function would be df2 by dx, right? Sorry, dx only, and df2 by dy. Now you see that the partial derivatives are, or there are four partial derivatives. Essentially, it's a matrix. First saying how, and first column showing how those two functions changes with respect to x. Second column saying how those two functions changes with respect to y. So when you have, eventually, when you have a vector input and vector output, a function which takes a vector value and outputs a vector value, the gradient of those functions, not gradient descent, but the gradient of those functions are matrices. Those matrices are called as, these are special matrices which are called as Jacobians. This is what we will learn in the next class. And then we will go from Jacobians to Hessian to maxima minima and Taylor series. Okay, so those are the things important, but just to in 2 minutes, this Jacobian is what you see here, right? When you have a vector input, vector output, there could be four different partial derivatives, and those partial derivatives arranged in a matrix, it is called as Jacobian. I'll give you an essence of Jacobian, what exactly it is, why it is important from ML point of view, and all of those things in the next class. But this is Jacobian. We'll learn about Hessian matrices. There are questions which might come from Hessian. This is important. We'll solve some problem from Hessian. There are questions which will be coming from Taylor series. Direct questions, okay? These are some of the most scoring topics that we have. So, Hessian matrices and Taylor series. Taylor series, just to give you an intuition in 2 minutes, remember you have calculators. In your calculator, if you have to find out the value of e to the power x or e to the power sine x, you can easily do that. Think of the medieval period or before that period, 18th century, 17th century, during 19th century, when all of these scientists were doing all of these calculations without calculators, right? They used to have had some sort of mechanism to find out the values. So if you have to find out the approximation of a function e to the power x, Taylor series is basically approximating some function which is smooth. Generally, it is used for non-polynomial function like e to the power x, sin x, log x, and so on. Approximating the value of the function using some approximation. Okay, so you might have seen sin x is written down as x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial, and then it goes up to infinite series. Log x has also a same sort of pattern in infinite series, right? Each of those and those formulation, let's say e to the power x also has a infinite series 1 plus x square by 2 factorial plus and so on up to infinity, right? So all of these things are actually an outcome of Taylor series, and that's why Taylor series is important, because if you have to approximate sin x at a particular value, you know that sin x can be used approximated using this function. Okay, just to show you that visualization, let's say drive, and this is just an intuition that I'm building for the next class, and then I'll open up for questions for the next 10 minutes. So Taylor's Taylor Taylor series. Yeah. So if you see here, if you have to approximate a function at a particular point, come on, open up. If you have to approximate a function at a particular point, you just can start from that point. Let's say that you have to approximate sin x. This is the first approximation, the first value. Second variable added, x cube by 3 factorial. Third variable added, x cube by 5 factorial. Fourth variable added. So Taylor series is basically an approximation, right? For all of any smooth function, you can use it as an approximation. Okay. Anyway, I'll open up for questions for all of you. We'll go into all of these things in the next class. Go ahead. Are you not muted?
The extra class will be on weekday or on weekend.
It would be on weekend. I mean, on Saturday, the way we have been doing it. Okay. It will not be on a weekday, obviously. It can never be it can never happen on a weekday. That's a mandate given to all of us.
Sir, one request, can there be a small session on a kind of a recapitulation of whatever you have taught with some examples on what questions, probable questions, not exact questions, but something like that?
Yes, definitely. We will have that. That's why the class on this entire class on the last class, basically it will go through each one of them, so that becomes easier for you to understand. Okay. So we'll have that. We'll definitely have them. If you see here, this is what your gradient is. You start from a particular point, you take a step towards the direction of minimum, and then eventually you will reach minimum, right? And that's what we looked at. But anyway, you will have those classes, and I would schedule one extra class on Saturday, and eventually we have the final class on Sunday. So I just have to, just to help you understand, we just have to go through Taylor series, Hessian matrices, Jacobians, and there is one part which is backpropagation. Okay, these are the 4 topics that we'll have to cover. I'm sure that we'll be able to cover in the next class, but given that we might want some practice, I would open up one extra class for all of us.
Sir, one question.
Mhm.
So we talked about this partial derivatives, right? So
Right.
in partial derivatives, we took some example of like X, Y, Z, or maybe two or three variables, right? So if we like take an example of this hidden layers in that DNN, so what is the like kind of variables that can go up to like uh, I mean in our example we just took X or Y maybe, but what?
See, neural networks, when you think of neural networks, you would eventually what you will be having x1, x2, x3, x4, right? You can have, let's say you are trying to model or you are trying to build a model just to predict, let's say that how many orders people would be placing on Zomato next day, right? So number of orders is what you are trying to or let's say let's go into something, let's say you're trying to predict watch time of Netflix using all of these factors. X1 is age, x2 is gender, x3 is location, and then so on. There are many different variables involved right now. So all of these variables would go into gets into these are the variables that you are using as, or let's say that you eventually calculate mean squared error, right? Mean squared error is what your target was and what your prediction is. Difference between them is squared up for all the predictions that you have. So you will have an eventually historical data set using which you will be making all of those predictions, right? So you would have historical data set with all of these x1, x2s as columns, and then all the data that you will be having. You'll have a target variable. The target variable is what you want to predict. What your prediction might be very off from what exactly is the target. So the idea is to minimize them. So you will use mean squared error. The good part of mean squared error is it's a convex function, a squared form, right? So it's a convex function. Now, because it's a convex function, let's say that in eventually in your, come on, stop. I don't know what happened to my cursor. I don't know what's happening to my cursor. Sorry about that. So if you are using a neural network, you have an output. Output is all dependent on your hidden layer. There could be multiple hidden layers. Let's say this hidden layer, this hidden layer, this hidden layer, and then you have an input, right? So you cannot change how does your output changes directly with respect to x1, x2, s3, or the weights attached to them, whatever you're trying to vary, right? Because your model is not to change x1, and these are the data that you have captured. Your model is you are trying to find out a non-linear model with respect to weights. So you would want to find out the weights attached to each of these variables or the weights. These are called as the parameters, right? So you would want to find out the weights, and these weights are not only the weights attached to inputs, there are weights attached to the hidden layers as well. There are weights attached to each one of those hidden layer connections, right? So because these are the weights, you would want to find out how does the output changes with respect to your input weights. But that input weights, they are all dependent on how does output changes with respect to your hidden layer weights. How does this hidden layer weights changes with respect to this hidden layer weights? How does this hidden layers weight changes to this? And then with respect to them. So basically, eventually it's a set of parameters that you have. Some weights here, some weights here, some weights here. You don't want to vary with respect to x1, x2, x3 because your model is already trying to see that variation. You would want to fit in the best possible W's such that whatever variation is coming out of the data, because of the variation, the difference between the target value and predicted value is minimal. You want to minimize that. So you would want to find out what are those W's. Think of it as a very simple problem. Let's say a simple linear regression problem, right? Y is equals to W1 x1 plus W2 x2 plus W3 x3 plus, let's say, B, okay, bias term. Let's say three variables are there. You have your in your data, you would already have y variable that you would want to predict. You would already have x1, x2, and x3. These three variables would already be there, right? So you have the data which is already there. You would just be changing from one row to another row. You'll be passing those rows and trying to see how does y relates to each row of the data, using this equation that you have, right? So because this is already known, this is already there in your data, this is already there in your data, the unknowns are weights W and B that you have. Basically, W is W1, W2, and W3 in this question. So these are the weights which needs to be known. So your idea is how does error changes with respect to weights, not with respect to error changes with respect to access. Okay. Eventually, you're trying to see how does error changes with respect to these weights which you have assumed in the model, right? So that's what you keep varying with in either your neural network or your simple models like linear regression or whatever types of models that you have, because you use gradient descent in every model that you have, right? Gradient descent is the crux of every single machine learning model. Beneath the models, you are doing gradient descent internally, and not in tree-based models and so on. But all the neural networks model that you see, whether you see an LLM or you see uh, image generation model or whatever you have, everywhere you see gradient descent happening in the back end. Gradient descent is so profound. Yeah, go ahead. Sorry.
This gradient descent right? So there could be chances where it could move beyond this global minima and it goes to other side of that convex function.
There are chances, yes. I mean,
So
let me
how
show it
to
to you.
deal with that?
You have to just take. I have not told you about. We have not actually. I have told you only about gradient descent. I use the concept of, sorry, I have only told you about gradient. I have used the concept of gradient descent to explain you gradient. We'll learn about gradient descent eventually, but the question that you're asking is all dependent on step size. If your step size is very high, then what would happen is you will evade the entire place. I'll just show it to you. These are the, I don't use it right now, but these are the things that I eventually created for my students 2 years back. So if you see
Step size as in that learning rate, that alpha.
the learning rate, yes, exactly. That's right. So if you see here on this visualization, this is the optimization thing. Some of you who would want to get intuition about this was created actually 3-4 years back when I was learning about the back end of the algorithms. So if you see here, I mean, this is a convex function x square plus y square, because you see that there is a only one minimum. I wanted to add a non-convex function as well, but let's say that these are the things that you will be learning later on. But let's say see that this is the gradient descent algorithm, right? You start from this point and you start taking steps. If your step size is large, right now the learning rate is large. Let's say that if your learning rate is small, the problem with learning rate small is if your rate is too small, okay,
It will
you
take
are
time to converge.
exactly right. So it might not even converge. It might just get stopped at some point. If you take too large of a value, let's say 0.9 or let's say 0.99, in that case it might also take too large, and let's say that it goes, let's say if I take 1, it goes beyond, let's say it just oscillates there. And let's say if I take 2 learning rate, it goes beyond it. It has gone out of of the valley that you had. Nice looking U-shaped curve, right? It has gone out of that. So gradient descent may escape the route as well if you take a high learning rate. But these are the things that you will be learning in the next session, series of sessions. We'll be though these lectures 8, 9, 10, they are heavily dependent on gradient descent. Okay.
Yeah, but Professor, you mentioned about this Hessian matrix, right? So that will ensure that we will always reach a global minima, right? That's my understanding.
Haitian metrics is, yes, it will tell you about where the minimum point is. It will not ensure that you land at global minimum. It just tells you, is it a minimum or not? It's Haitian metrics is just to ensure that everywhere around that point, if the function is increasing, so it just tells you where the point that you are sitting in, it's a minimum or not. It doesn't tell you whether it's a global minimum or not, and you
Okay.
will eventually learn about it. Okay. Okay.
Hello,
I think, yeah, go ahead.
sir. I have one doubt.
Yeah, yeah.
It's maybe it's very basic, but question is, for in case of a linear regression, we have suppose we have 10 features, x1, x2 up to 10. So after we compute our gradient descent, we arrive at w0 w1 to W10. So we finally get the equation as W1 x1 W2 x2. We arrive at the final equation. In case
Right.
of a artificial neural network ANN architecture, we have in between hidden layers also. So hidden
Right.
layers, we have those perceptrons inside. So we finally arrive at our model. So in this case, what will be the equation? Because in the inputs we had, suppose we had 10 inputs. Inside we again had, suppose in the first hidden layer we had 8 perceptrons. After that, suppose 4 perceptrons, and finally output one layer. So here the equation will not only be the initial W0 W1 x1. After that, because our hidden layer is also there, right? So finally the w's which will we will arrive. So how we will write the final equation in case of a ANN?
And see, if there is no, firstly, there is no final equation. It's a chain of things that you are doing. Sorry, my board somehow. Just give me a moment. So what happens there is, if you think of a neural network, you have this arrangement of neurons, right? And let's say that you have an output. Now, this is the first hidden layer. This is the second hidden layer. By the way, you can actually do this in tensor. Let me not write it. It will take time. TensorFlow, neural network playground, or deep learning playground. You might have already seen this thing. So if you would want to learn about it, go ahead and explore this. This is a good place to actually learn about how does the entire thing happen. Let's say that you have two different inputs. You have too many neurons in first layer. You can add as many layers that you would want, not more than four eventually in this case, because obviously this was created for intuition purposes. So if you see here, X1 and X2 are inputs, they get combined here, right? So some W1, these are the weights that you have, right? Now, what happens is all of these weights get combined with whatever your inputs you're getting, you are combining them here. In this particular place, based on whether the signal is very strong, you basically do an activation function. You try doing some non-linear transformation of your, basically, if you think of everything that you are doing is Wx plus B, right? W1 x1 plus W2 x2 plus and so on plus B. So this is a linear function, right?
Hmm.
When you pass this into an activation function, what happens is activation function changes this into either 0 or 1 kind of activation functions which are there. They are ReLU, rectified linear
Correct.
units, right?
Correct.
So rectified linear units, the function are max of 0 comma x. If x is negative, it will just pass 0, right? So if x is
Agree.
positive, it will pass the positive value, whatever that is, right? So if you think of in these case, in this particular case, and a transformation is happening because of activation function and then going to the next layer, getting multiplied with the weights. Whatever activation function output that you are getting here, they are all getting multiplied with the weights again, going here. Some nonlinear transformation here of activation function, going again to the next layer. So if you think of, it's an arrangement of all of these transformations happening at every neuron. If you have to write down one single function, you cannot do that, because eventually in your deep learning you have a very huge deep neural networks, you have a huge neural network, right? You would have many different hidden layers. Right now we have only a flexibility to add six, but let's say that even with six, if I have too many neurons in every layer, this becomes huge problem to see eventually, right? So this is, you cannot relate your output with respect to your transformation which is happening everywhere. What you can only do is how does your output changes with respect to your the first neurons which is directly connected to your output layer of neurons or hidden layers. Then how does that hidden layer is connected to your previous layers, because you have these weights, all of them here, right? So you would see how does the output changes with respect to these weights first, and then how does the output that you are having here changes with respect to these weights that you have here. Then how does the output that you have here, how it changes with respect to these weights. So this is all connected, right?
Yeah.
So you eventually don't look at one single formulation, just like how you see at linear regression.
Got it.
One visualization that I could show you is, see here, This is the linear algebra part. This is what eventually, if you will get to this part, you will understand everything about neural networks, right? So if you see here, what happens in neural networks, you are just doing, let's say, this is what you are doing, wx plus b. Now I told you it's all matrix multiplication. What matrices does? Matrices distorts the spaces, right? It gets distorted like this. Now post that, what you do is you apply some hidden layers, ReLU. What ReLU does? It it changes, transform the space, makes linear non-linear. See the transformation linear to non-linear happening. That becomes non-linear, right? Now once that happens, you just start working on the output part, whatever it is. So there are various different aspects of seeing that, but you will learn about it. So we have so many classes. We'll go into the deeper aspects. You have just started to look into from the perspective of neural network. How does chain rule gets applied to neural network? But we'll get into more details of it. How does it gets affected? Okay, don't worry about it.
Thank you, sir. Thank you.
Okay. Okay. Thanks everyone. Thanks for joining. Okay. Thank you. Thanks all. Stop. Thank you everyone.